Hello and welcome to the presentation, Sources of Systematic Error, a Cognitive Ergonomics Perspective. We'll be talking about systematic errors in safety instrumented systems and SIFs. Here the image on the left is the frame we're going to be using. So these systems are all made up of physical, human, and organizational elements. And B, a researcher out of Berkeley, has identified through major accidents that societal elements can contribute an additional 2 orders of magnitudes of risk, and so we're going to be talking about the potential effects of those. The mnemonics I'll be using is P, E, H, E, O, E, and S, E. So physical elements are what you would expect. Human elements, primarily we're talking about competency, so this is a skill and a knowledge competency. Organizational elements of that group, we're going to be talking about procedures and training and competency management. Societal elements could include governance, laws, regulatory regimes, demographics, economic forces, and the existence of industry standards, and meaning this standard. And the scope is look at systematic error with essentially governed by the standard. And here the shaded area is just symbolic, and saying these are the things that are captured in the standard at the time. You know, so everything is not captured as yet. So this is really a question. So the scope I'll be talking about human cognition, and actually to give you kind of an introduction to some of the cognitive things that affect SIF performance and error. We'll talk about errors associated with organizational elements, so these could be components, procedures, and might be attributed from the standard itself as to how they're being addressed. We'll talk about errors attributed to safety critical tasks, and here there are many such tasks in these systems. We'll be talking about when we're in bypass, and we'll be talking about those attributed to the SIS interfaces, so that's section 11.7. And we'll be talking about some of the societal elements that are influencing factors and the mechanism on how they could contribute to error, and those attributed to business downturns, regulations, and the standard. So humans have 2 cognitive processes, automatic and conscious. These have been well researched. There's quite a bit of information on both of these. Some of the unique things is the automatic processes are mostly hidden to our conscious processes. Conscious processing were late add-on or evolution, and create some interesting interactions between automatic and conscious processing. So automatic processes bias conscious processing, and you can have a conscious process that interrupts an automatic process. So it's quite interesting. So automatic processes are always on. 95% of all of our daily activity fall are governed by these processes. So speaking, recognitions, skills, those are all governed by automatic processes. It's normal operation, it's automatic, continuous, it's effortless, so we can't really feel its function when you compare it to a conscious process. We know we're thinking. Automatic, we don't. And it's very fast. I could look at something, and within 75 to 100 milliseconds, I can actually have a recognition and an understanding of what I'm looking at, and maybe some response associated with that. And it's one of its main attributes is a recognition engine. And you know, James Reason says humans are furious pattern matchers. So the way it works is sensory information comes in, it's bouncing off what we hold in memory, and then popping that memory up, and that provides the recognition. Conscious processing, less than 5% of what's happening in your day are actually governed by a conscious process, so that we all might be surprised with that. It's slow, linear, and it's sequential cycles. So, you know, interference in the sequencing of an activity could cause all types of failures. Highly effortful, so if you've been a HAZOP, and in day 2 or day 3 you're already feeling burnout, well, you're trying to pay attention 100% of the time, and as compared to 5%. And so it's an unusual thing that gets us tired quickly. Daniel Kahneman has characterized as conscious processing as lazy tendencies and seeks cognitive ease. So a conscious process has a fixed capacity, and each of us are on our own journey as to how mentally we utilize that resource, because you're trying to hold something in reserve. The normal pattern for all of us is to, there's inherently ways that it seeks to reduce demand, and so confirmation bias is an expression of that, and which works pretty well in the normal world, but in the technological world it can be problematic, and it's realized by attention and working memory. So humans, when you talk about clock time and are we reliable internal sense of clock time, the automatic process is not at all. It just doesn't have a purpose for a clock. On a conscious processing, we're limited as to our internal accuracy of monitoring clock time. So detecting risk is automatic process has no capability to detect risk. It does detect danger, those that are learned, but not risk. So a sensitivity to risk is only if you actively make yourself think about that. Automatic processes do not validate response before action. It has no mechanism to do that. So if it's not trapped by a conscious process, that impulse to act is driven by automatic processes. And automatic process is the world of skills and habits. So all skills start out as a conscious process. We have to actually think about it. It's clumsy, it's effortful, and through repetition over time, it starts to develop into an automatic process. And over the course of 2 to 6 months, it become automated. And so now, as we're trying to go the other direction, how to break a bad habit, it requires this continuous conscious effort each time, and that's why it's so difficult to break a bad habit. So mental models, here is the way humans understand information is the way it gets stored. So it's not like a computer. It's not storing facts. It's storing our understanding. So that's our own little expert system, which has degrees of accuracy and completeness. So memories are live files. So they are subject to change with every recall. And, that's so that feature of our memory is the things that allows us to be adaptable. And of course, the one thing we don't know that we don't recognize those changes over time. And, if you have a highly emotional event, that memory could imprint in a single incident. So, how does this play? Well, let's say I'm an operator and have excellent, normal, good practice, safety conscious, something changes and that person takes an unsafe shortcut and nothing happens. And later on, the same circumstance comes up, and again, I take that shortcut, and nothing happens. Well, over time, that mental model is drifting. So that mental model, which is a key part of essentially our SIF design, it's mindware, but it drifts over time. And so at the sharp end, people doing work are constantly pushed by production demands. And those production demands, if they're not balanced by, say, a safety culture and daily safety push, well then entropically, the mental models are going to shift to the production direction. So our conscious processing was realized by attention working memory. That term working memory is unfortunate because that is our conscious processing. It's enabled by executive functions and relies on short-term memory stores. Here, this is the thing that actually allows us to self-reflect, analyze, check actions before we take them, or if we're working at a high tempo, it consumes working memory. So you can see all these things are competing for the same resource. So because it's slow, it's limited to its ability to take in sensory information. So the 11 to 13 million bits of sensory information that comes in, the most you can consume is 10 to 50 bits per second, and it's normally more like 1 or 2. So when you think of the gorilla experiment, here is only half the people saw a gorilla walking through the exercise, and actually when I think about this, I'm surprised that 50% did see it. Yeah, it's just a quirk of our working memory. So short-term store is limited to these 7 chunks of information, and actually current research thinks it may be less than that. And the unique thing to consider in a design is the stored duration of that could be limited to as little as 10 to 30 seconds without refresh, which means that I have to constantly come back to it and think about it. So unlike RAM in a computer, here is that information stays there until something replaces it intentionally. Short-term memory store is if I don't think about this, essentially it disappears and it's gone. So attention is our ability to direct this working memory to an object and bring it into our mind's eye. And it is, and we can only attend to one thing at a time, period, hard stop. It's a hard design constraint. Here, as we think we're multitasking, our attention is switching between what we're attending to, and there is a penalty for switching. So now we're going to move on to organizational and human elements, and specifically the listed here. And a little bit of background, just to kind of emphasize terms. You know, we talk about knowledge and skill. These are components in a safety critical task. They're every bit as important as, say, a transmitter. So knowledge is the knowledge one must have to correctly perform a task, and a skill is that capability that you need to perform a task. So knowledge, you know, here we basically all dominantly rely on memory. So knowledge is something that has to be stored in the head. So essentially these are memories and mental models. And skill is that thing we actually have to learn through practice. And you know that's an automatic process. And then we talk about competency. We're talking about these very explicit knowledge, skills, or aptitudes that are required to be successful in performing a safety critical task. So we come to training, and you know this comes out of the mentioned book. These are globally recognized experts in other industries, so in some ways I may be 10 to 20 years ahead of what's standard in our industry. And the headers across the top are issues that they see are essential to training. And so these these activities are actually processes. And so if there is a deficiency in the process, the product of the process is going to be also deficient. So, you know, now you have sources of systematic error. So when you look at training content, another thing that's important is the recommendation is to use a task analysis to identify what training content should be. And the other side of these is, since we're talking about processes, well, now we're talking about an overarching program in the organization that's providing these processes that needs to be mature and published, you know, so it has a confirmed efficacy. So when you switch up to procedures, again, same book, same authors, the procedures and processes that are headers at the top. Same thing, these are all processes. And just like training, it's the same recommendation to create a procedure. You know, they recommend using a task analysis to identify what procedures are needed and what the content of the procedures should be. And again, these are recommended that, you know, here you got an organization that's conducting these processes. They need mature and published processes. So now think about a SIL3 system. And let's say someone wants to provide and develop procedures and training. Well, if they don't have mature and published processes, to be honest, they're not competent to do these, you know, because now you don't have any assurance that what they're going to produce is actually going to be something that meets the efficacy requirements for a SIF. So now when you look at the standard and you see these terms, procedure, training, skill, knowledge, all of these says there is a human, and you only invoke these when there's a task. So basically, every use of these in the standard is invoking a safety critical task. And you know, here is the way to look at something like a procedure. A procedure is a SIF component that's every bit as important as, say, a transmitter, but you know, the failure mechanism is different. So you know, if I have a sensor fail, and you know, now it fails and it reveals, and it reveals right away. A procedure now a procedure invokes a Swiss cheese model, and I have to add some other conditions to lead to failure, but nonetheless it leads to failure. And, now is when you look at the standard, which is really a hardware-centric standard, essentially what it's doing is pulling, say, something like a procedure out of the air and tacking it on to a physical activity within a standard. And the question is that these things have their own development processes and concepts that are actually really not talked about in a standard. So there is a flow down, and they're all rooted in a task analysis as the requirements basis for their development. So, think about is what would happen if I develop a safety system and I never wrote a design basis. You're going to have all kinds of errors all through the system. The same is actually true as if I don't do something equivalent to a task analysis. So all these are elements that are attributes and components in a safety critical task. We're going to talk about the third one. And so here, a safety critical task, in the O&M, here we're talking about these types of activities that are listed. So, and we're going to be talking about some of these in some detail. So, in the standard, here industry guidance standards, the more advanced ones, are all recommending the use of task analysis and creating this frame around safety critical task and task design. But when you look at the standard only has, part one only has one reference to the use of task, and that's in 11.2.6, which is a statement by itself from a cognitive ergonomics. Could have all kinds of problems with interpretation, and then when you look through the O&M section, whenever it uses the term activities, or where it uses terms of activities, most of those you could have substituted the term safety critical task. And something as vague as an activity doesn't have a design concept. A safety critical task does. So here, without having that in there, it doesn't imply that you need to do development of this task. So those are sources of likely contributors to OE attributed systematic error. You also find a standard, it has somewhat random use of the terms training, skills, and knowledge. So there's places where, it'll actually put the word skill. It's obvious from a cognitive ergonomics perspective, they're talking about skills and knowledge. So now the question is that in itself, for the reader that doesn't have a lot of experience on cognitive ergonomics, may actually miss the importance of what's being said there. It may just say, well, I gotta define a skill, but it says nothing about knowledge, so I'll just go ahead and crank it out that way. So now we're going to move into bypass in terms of OE and HE design. So let's talk about an accident in Deepwater Horizon. Essentially you had a SIF, and the SIF was a flammable gas detection, and what it was is it was actuating a tripping HVAC, stops fans, and closing inlet dampers to a series of rooms. In the rooms were all these gas turbine-driven power generators, and so these generators were actually, their air runs were actually inside these spaces. And then adjacent to that, you had electrical rooms that had low and medium voltage MCCs and switchgear. And so the idea is, if we had a blowout, here is you take gas and you prevent from sucking flammable gas into these non-classified spaces and into the inlet of the generators. But the evening of the accident, for the person on duty, from the first pre-alarm that came in on gas to the point that actually as you had actually met the gas activation trip point, and actually as now you have all kinds of gas alarms that are activated, was less than 1 to 2 minutes. And here is in the process of this short time, the person never activated the ESD, and it's not clear that it's not clear that this person knew that several minutes prior that the drill shack had realized that a kick was in progress and a gas release was possible. So the consequence of that, HVAC pulled flammable gas in the rooms, the gas ignited, and the explosion in this space was catastrophic and unrecoverable. So from the time that the kick was first detected, and it had been going on for some time, but from the people on the facility knew, well, basically from that point to this explosion was 8 to 9 minutes. And from the time the operator first saw the first pre-alarm to the trip status was 1 to 2 minutes. So it was extremely fast. And now the also effect of the generators, they had triplicated overspeed protection, and here is another societal element that a regulatory may have been a contributor as to how could all of these have failed, and it may have been attributed to how regulatories, the requirements of how they do annual checks of these. So the testimony of the operator claiming testimony that they weren't trained on how to respond to the alarms, didn't seem aware that there was a response to manually activate a shutdown function. There was questions about should a person in a drill shack have activated this alarm, and now it's clear that it wasn't clear who was doing what. And now there's another problem that's I don't think is very well recognized in our industry. That here if I have a SIF type where the detection information essentially is inferred measurement of the actual risk, there's an inherent problem with that. So on a flammable gas detection, the operator is getting percent LEL. The actual risk is the gas ignites, and I have a temperature load or an overpressure load on a receptor. And so now is in the design of a facility, I have a gas cloud of a certain size in a certain place, and on ignition those thermal loads and overpressure loads are the basis for design. And the question is, does the operator know that? And so does percent LEL actually cognitively even make sense? And of course, so when you look at the response time, was that realistic? And now the other kind of hidden thing when we think about mental models is chances are these events, gas release, pass and they never ignited. And so the operator may not realize that their mental model being shifting is it's not really a risk, because nothing happened. And so that could be a person's false understanding of risk, just because of prior events. So now we look at what does the standard require in terms of bypass design, and it's using the word compensating measurements, which really is a euphemism, that doesn't have a meaning from a design perspective. So the question is what should happen from a PEOEHE design, and so if you were considering it from a holistic design process, would that change design display requirements, OE requirements on say knowledge? So does that change HE competency requirements? If I have a PST of 5 minutes or less, what effect does that have? Does it change decision support features? Here is if you're trying to do something very fast, you're talking about a skill. So you're talking about muscle memory, and from a training perspective is you're not going to get that in a classroom setting. You're going to get that into a dynamic, time-pressured setting in terms of drills. And now the question is if you're going to manually activate the SIF, through what? Where is the target? Is an HMI target? Is it different from the manual ESD? So on the bypass side, these bits are scattered all through, but actually it's a single integrated design process. Because now this essentially what happens is when you put it in manual mode, it becomes an active human barrier, or you could view it as a safety critical task, and it needs designed holistically on all these parts, and that doesn't happen. And then the question is, then what happens if, is it different if this is a SIL3 system? So the design model for active human barrier design, and it's the same for safety critical tasks. CCPS, their standard model is this detect, decide, act model. So that applies to a SIF, alarm IPL. It's also the same for safety critical task. And here, the more advanced standards add an additional component. Many of them are adding Inslee's situational awareness model. and they could be other variants. But the key part of this is it adds a box between detect and decide, and that box is comprehension. And so the question is, in order to make a decision or guide action, what do I need to know? And as soon as I say that, now this is explicit knowledge requirement, that put into procedures, and now it becomes an operator competency. So this is the form you actually really need to use and actually to fully design PEHEOE. And the functioning is what's different about current design. We tend to go head to tail. The right way to go is tail to head. Define all the actions, then define all the decisions, and there's always more than one, no matter what. And now is what comprehension do I need to guide decisions, and now I can finally say what information do I need to guide all of that, and that information load is going to be probably more than what we do now. And so now all of these now, when you think about if you're going to do a cognitive design approach, now all those wrap in differently to each one of these boxes. So failure design at this level, you're guaranteed to have cognitive ergonomics errors in the design that could be expressed through PE, OE, and HE. And so the consequences are very diverse on what their nature might be. So this figure, we're not going to go through it, but these are all the components from, say, an HE, the HE perspective. And so if you're designing safety critical tasks and you're not considering all of these, you could have a gap in that element. So any one of these you miss, don't be surprised if it creates a gap that gets expressed as a systematic error. So let's look at an example. Say an alarm IPL, and let's say the alarm, it has a process safety time of 30 minutes. So we think because we have a long time, it's actually going to be reliable, and that's not the correct thinking from a cognitive perspective. Here is they even have a name for what's being asked. Because when an alarm comes in, you're asking the operator to remember something in the future, and here if you talk to James Reeves, and it says this is definitely something that is not reliable for humans. So we unpack that. Now as you break this down is, the alarm comes in, the operator places that placeholder in short-term memory, so I'm worried about it fading if I stop thinking about it. And then humans don't have their temporal capability does not include clock times. So if you've got to track time, you really have to look to an external clock. So now as the operator may have said, I'm going to wait to do this because I want to attend to something else, and I'm going to remember to come back to it, there's a good chance it won't. And if these stack up, some of these are actually just not going to happen for all of these reasons, and the operator is not going to understand why. But from a cognitive perspective, it's very obvious as to what the mechanism is. So here is a simple thing. If I've taken a risk reduction of 10 for alarm IPL, the idea that you're actually going to achieve that reliability without doing anything, knowing about these attributes. Here's something you do is as a PSD counts down, if they haven't performed the action response, then you actually have to, should actually have an alarm, to bring the operator back and say, I got a pending action. And if you get to the end of the PSD and you still haven't, then you really need to consider automating the final elements to their safe state. So how are OE and HE addressed in the standard? Well, it's actually very thin because again, each of these have their own design cycle in modern good practice, and the standard doesn't really reflect that. Essentially, they're just tack-ons. So 11.2, which is a kind of an odd statement. Here, if you're going to fix the standard to add safety critical task functions and task analysis, it could be reworded to talk about the scope of what it's addressing, and it's a hook into part 2, and here part 2 could introduce task analysis and safety critical task design at the detect, decide, comprehend level instead of an HRA. So it proposed an HRA, but the question is, why would I do an HRA if I actually haven't done primary design? And essentially, when you do the task analysis and you go through those steps, those are things that are a design basis level activity. So again, now if I would I actually do a SIS design, and I didn't do a design basis? Well, essentially, from from a cognitive ergonomics perspective, the standard actually is skipping this aspect of design for OE and HE. So there are sources of systematic errors. The types we're talking about, it's actually much broader than that. But and actually, it could be a PE design error because we could talk about a tool we're using, an environment, and the question if it's fully specified, is it usable in that environment? So let's move on to SIS interfaces. Here are the types of things that are mentioned in this section, and I suppose you're aware that Part 1 allows more, and Part 2 is more constrained, so they seem to conflict. So from the way I viewed it from a threat perspective, since this section covers operator interface, but it also talks about essentially the boxes that hook into the SIF and the SIS. So from a threat perspective I view it as how do these boxes threaten the SIF function or SIF integrity. So work within those boxes, say in asset management or safety critical tasks, right? Because a mistake in one of these boxes could change a function or change information that places the SIF in jeopardy. But here, this section really doesn't link into safety critical tasks or even into requirements for procedures, training, skills, and knowledge and competence. So that in this piece of the standard, people that don't really think about it don't think of that as a threat source. So what I've done in when I write safety requirements specs, and we've all evolved in how we do it, is in this section I take a little broader view as to the things to be considered in this section, and then essentially would do a simple risk assessment process where I go through each box and said each box, what are the potential threats to the SIF function or integrity? And they could be cyber, or they could be intended or unintended changes. So now I have a risk, and the question for each one of those is, what mechanisms am I including in the standard or the SRS as the mitigation for that? And virtually most of these are mitigated by administrative controls, so things like user access and authorization, or for cyber events, it's software backup recovery and software management. And I think we're all aware software management is a key weakness in most organizations. And the question is, how often does a facility actually attempt to do a recovery to make sure their backup recovery is going to work? So since these solutions are often breached or ignored, they are a source. And from a cyber perspective, if someone's going to do a cyber attack, get into an asset management system would be really problematic. So let's move on to societal elements, influencing contributors to systematic error. So, one is the negative outfalls from a business downturn. And we know how the effects of this ripples down to people at the sharp end. I could have lost a key resource that's saying managing and repairing a SIL3 system. A lot of times I've gone from 3 people down to 1, and now you're expected to do all the work. I could change in who you report to, and they have a different mindset. So all these could have a negative effect in both. And again, as your mental models are affected by what affects you when you're in the performance of activities, so they can change your mental models and also change your behaviors. And so, these are a contributor to this drift of failure we talked about earlier. So they're all sources of systematic error, and I don't think these are accounted for. And of course, the really interesting one is, the unintended behavior in organizations in response to regulations. So whenever you see it, either in operations or in a project, they seek to push against a regulatory requirement that's a gap or a lax. They're going to poke in areas that are have the potential to create new hazard scenarios and have contributed to accident events. So So, this is a source of risk that's missed in a risk assessment, that B would say is, these might be the kind of things that may actually increase the true risk by several orders of magnitude. So you look at Deepwater Horizon, they were allowed to make late changes, last minute. It's difficult to know, and regulations actually allowed them to do it, and that was a contributed error. The Boeing 730 was a really classic case. Boeing, a competitor, had created a new plane, so they wanted to create a new plane quick. And actually, as the regular form says, you can do quick, as long as you don't go outside, and we have to recertify. So they were trying to keep their design within this recertification constraint. And of course, as it got deeper and deeper, that design got more convoluted and went well past of what was permitted. But they used that, and of course, they delivered an airplane that was deeply flawed. So now let's look at another example. The procedure, how do you drift in procedures? Another causal event in Deepwater Horizon. When a kick occurs, the safety procedures say that you need to line up the well through a divert system to overboard lines, because if you get gas above the blow-up preventer on the ocean floor, there's nothing to stop it. And what they have done in practice is to line up a low pressure, low capacity vessel instead. And that vessel, its purpose under certain conditions was to separate gas from returning mud. Well, the consequences of doing that is within 1 minute after lining this up against this kicking well, you had flammable gas coming out of the mud gas separator vents. One of the vents was goosenecked down to the drill floor, and so now it's directly into the inlets, air vents to the HVAC, pulling into the electrical rooms. And of course, once it was pulled in the electrical room, very quickly you had this catastrophic explosion. So from the time they lined up the mud gas separator to this explosion was 4 minutes. So very fast dynamics. And this mud gas separator, essentially, the other aspects of it is it diverted gas in a lot of different spaces around the facility, that caused other types of releases. So essentially, it was a exponential multiplier of the hazard by how it actually the effect it had. So the question is, the operations folks used this, and they thought they had a reason, and they thought that actually this deviation was safe, and it's not clear what the true reason was, so it could have been as well. Most of our kicks are minor and short-lived. We catch them before we have a blowout. So we're going to catch the mud, which is expensive. Or maybe we didn't go the overboard lines, and so now is no oil got to the ocean. Oil in the ocean is a sheen. That's a reportable event. The question was that the reason. So now the last one is the unintended effects of an industry standard. So you look at the systems today that are being used in SIL3 systems, and so using a PLC essentially to replace a larger flare in the 1980s and 1990s was considered bad design. But the standard has now normalized the SIL3 system, and here the expectation is people follow good practice, but in the actual behaviors, I think we've all experienced variants of these. There are still some that actually view this as, well, if I can use a SIL3 system to save money in a project, let's go for it. And the other case is, we've all seen instances where something went bad in the design process, they got boxed in, and now the SIL3 system is the go-to solution. And of course, and they jam a SIL3 system in. And when you look at the things we've covered, the cognitive ergonomics side, there's going to be a number of these SIL3 owner-operators that are just not going to have the infrastructure or the technical capabilities or the management in order to reliably sustain these over time. So these systems might fail. So that concludes my presentation. Questions?